Welcome, friends. Today we shall be dealing with influence line for simply supported beam, and we shall be doing an illustrative example to analyze the maximum bending moment at any cross section along the beam. And in doing this, we will take the first one. We are considering 2 points. We are considering point 0.5 L along the beam. We are considering point 0.1 L along the beam, and we also consider point 0.3 L along the beam. Now, the beam in consideration is a beam of span 20 meters. Okay, so if our span L is 20 meters, we are going to consider the first point, which is the midspan of the beam, the point 10 meter, which is 0.5 L. So taking it from 0.5 L, which happens to be our midspan, we are going to have a unit load applied at that point, 0.5 L. When a unit load is applied at point 0.5 L, we have a unit load applied at point 0.5 L. When we apply unit load at point 0.5 L, we'll have the moment diagram to be as this. This moment diagram is also called the influence line diagram. And of course, the value of the point load at the midspan is PL over 4. If we do PL over 4, we're going to have 5 kilonewton meters. All right. Now, the next step we're going to take is application of the loads. Now, the load we are going to be considering is a HB load from the BS5400 and the BD3701 code, British standard codes. Now, the vehicles, like we know, is made up of 4 axles. Each axle comprises of 4 wheels. And let's call the load on that each way P. So we're having 4P in each axle. Now, I've named the axle like you've seen on the board. This is axle 1, this is axle 2, this is axle 3, this is axle 4. Now, once we want to calculate the moment at point 0.5 L, what do? The first thing we need to do is to drive this vehicle on this beam. Now, the direction of our movement matters a lot. It determines the magnitude of the moment that will be induced on this beam. Now, let's say we are driving from our right-hand side, which is from the support B side, to our left-hand side, which is on this other side. Now, this vehicle, we have the front axle to be as 1, the second axle as 2, the third axle as 3, and the fourth axle as 4. Now, the spacing of the vehicle, 1.8, 6.1, and 1.8 respectively. Now, how do we obtain the moment at this point, which is 0.5 L point, where L represents the span of the beam? How do we do that? The first thing, we'll place the first axle on this point. When we place the first axle, if we're driving from this direction, we'll place it here. This is the arrangement of the vehicle on this beam. Now, when we do that, if from here to here is 10, of course, we know that what will be left of this vehicle when the first axle is here will be 0.3. And from here to the third axle will be 2.1. And from this support here to the second axle will be 7.2. So having known that, that of the third axle we know is already at the point 10 meters. Okay. So what we are going to do is to calculate what we call the ordinates of the influence line. And what are the ordinates of these influence lines? The ordinates are the values of moment at when a unit load is applied on that spot, as it is on the diagram. So the ordinates are ordinate Y1, which represents the peak, the maximum moment at that point, which is 5 kilonewton. We have gotten that. What is unknown here is ordinate Y2, Y3, and Y4. All right. So if ordinate Y2, Y3, and Y4 is unknown, we've already known the distance 6 to each of these points from the right-hand support. What we'll need to do, we make use of what we call the similar triangles. The similar triangles, we are going to have it as this. Of course, Y1 is known to be 5. Of course, by similar triangle, the ratio of Y2 to 5 equal to 7.2 over 10. We'll have that Y2 to be equal to 3.6. So if Y2 is equal to 3.6, we continue with Y3. Y3 will be also Y3 over 5 divided by equal to 2.1 over 10. We do it accordingly, and we'll have all these values. So we now have that y2 3.6, y3 1.01, and y4 0.15. Of course, we already know what y1 is from the moment formula PL over 4. So the next step we are going to take is to calculate the moment due to each of these loads on the beam. Now we'll start with the first axle. The load on the first axle is 4P. So the moment due to the first axle, let's call it M1. So if we have M1, moment due to the first axle is M1. M1 is equal to the load on the first axle times the ordinates at that point. If we do that, the ordinate is 5, the load is 4P. So we're having 20 P's. The second is the second axle. What is the ordinate of the second axle is y2. And from here, we have y2 to be 3.6. So what it means is that 3.6 times the load on the second axle, which is 4P, and it gives us 14.4P. Now we'll go to the third axle. The third axle, we have the ordinate y3 to be 1.01. So the moment at that point, due to the third axle, become 1.01 times the load at that third axle, which is 4P, gives us 4.04P. The last, which is the load on the fourth axle. Of course, we know that Y4 from our analysis, Y4 is 0.15, and the load on this fourth axle becomes 0.15 times 4P, and it gives us a 0.6P. Now, the next thing we are going to do, the total load by principle of superposition. We know that the total load for superposition is 20P, 14.4P, 4.04P, and 0.6P. When we sum up that, we are going to have 3.904P kilonewton meter. So this is the load, this is the moment at this point 0.5 L due to this series of concentrated load in the first instance. There's a first load arrangement. So what we are doing is a sort of trial and error. So this is the first moment we have. But we are not too sure this is the maximum moment that this series of concentrated load will produce. So we are going to try another position. Now let's try the second position. The second position is this. In this case, our vehicle has driven to this point, and we now have the first axle 1. Axle 2 is now at the point 0.5 L. So when axle 2 is here, remember the moment remains as it is when a unit load is applied, 5 kilonewton meter. So when the second axle comes on this point 0.5 L, we'll have the arrangement like this. You see 6.11.8. Now the same principle goes on. We make use of similar triangle. Let's call this our first axle. Our first axle, okay? Let's say our first axle, let's call here Y2, okay? Let's call here Y2 this time around, Y1. So our first axle, which is axle 1, moment due to axle 1 will be ordinates of the influence line at points at axle 1, and that ordinate is Y1. And by similar triangles, we know that from here, from A to here is 8.2, and from here to here is 10. So if we go by similar triangle, it becomes 8.2 over 10 equals to Y1 over 5. And when we do that, we have that Y1 to be equals to 4.1, and that is the ordinate at this point Y1. So if we have that, the next thing, the moment, we can do the same for the rest. We have from here to here, ordinate Y4 is from point B to here. If we do it, you will discover that it's 2.1. Y, the distance of this ordinate from B to Y3, we have it at 3.9. So by similar triangle, we are dealing with this particular triangle now. When we deal with this particular triangle, it becomes what? It becomes Y3 ratio 10 equal to Y3 ratio 5 equals to 3.9 over 10. That will give us Y3 as 1.95. We will do the same thing for Y4, and we'll have Y4 to be 1.05. Okay? All right? So this is what we have. We've gotten Y1, we've gotten Y2, and we've gotten Y4. All right? So So this is our Y4. 1, 2. Y2 is 5. Let's call our Y2 is 5. So, sorry, this, let's call here our Y2 here. Let's call our Y2 equal to 5. Our Y1 here's our Y4. Okay. Here's our Y4. Okay. So our Y2 is 5. Our Y4 is 1.05. So moment. Now let's get the moment due to each of these load on this beam. Now due to ASU1, moment due to ASU1, the ordinates at ASU1 is Y1. So it becomes Y1, which is 4.1 times the load on it, which is 4P. So we have it as 16.4P. The second one is Y3. Let's deal with Y3. Y3 is the ordinate under this 4P load. So, and that is 1.95. So we can now say that moment due to ATO 3 becomes 1.95 times 4P, which is 7.85, 7.8P kilonewton meters. Now the next one is Y4. Y4 is here. So the moment of Y4 is moment due to ASO 4 times ordinate at 0.4. So if we do that, we are going to have moment due to ASO 4. The moment due to ASO 4, all right, moment due to ASO 4 is 1.05, which is the ordinate at ASO 4 times the point load, the load at ASO 4. That will give us 4.2P. And we also know that M2, which is here, is equal to the moment will be moment, M2 will be moment due to ASO 2. It comes 5, the ordinate at ASO 2 times the load at ASO 2, which is giving us 20P. So by the time we do a summation of this, we are going to have 48.4P kilonewton meters. This is the maximum moment at this point. Now, we are going to stop here. We are not going to test ASO 3 because when you bring ASO 3, when you drive down this wheel, ASO 3 comes here, it will be of the same thing as this, but in the other direction. So there's no need of testing ASO 3. When you put ASO 3 here, it will be similar to what this arrangement, since the beam is symmetrical. All right. So we are not going to do that. So from these two positions, we can conclude which is the maximum moment. We have 39.04. We have 48.4P. So from all indication, it's obvious that the maximum moment will come when the load is arranged as thus. So the maximum moment is 48.4P. This gives us the maximum moment at this point, 0.5 L. So I believe you've been able to understand it from what I've just illustrated. Now the next one, I'm going to do the second point, which is 0.1 L. If we look at 0.1 L, if 1 L, you will observe that we are dealing with a point which is about 2 meters from the left-hand support A. So if we take the bending moment of this, remember that the bending moment of this is PAB over L, the moment at this point. So if you do that, you are going to have the unit load, which is 1 times 2 times 18 divided by 20. That will give us the unit, the moment at that point. At that moment will give us 1.8. So this is 1.8 here. So now let's go over to this and let's calculate the positions of these loads. So we are taking 0.1. Let's look at it now. The bending moment diagram due to this is 1.8. You can see the bending moment diagram on the board here. Now our direction of travel, let's travel from the right hand side B, support B. Let's travel to the left hand side of this same support. Now if we are traveling for support B, we are traveling to support A. The moment at this point is 1.8. Now let's place the first ASU, which is ASU 1. Like we did in the first example, we have ASU 1, ASU 2, ASU 3, and ASU 4. So if we place ASU 1 at this point we are interested in, which is 0.1 L, which is also equal to which is equal to 2 meters away from support A, let's place our ASU there. If we place our ASU there, we'll have it as this, the arrangement as thus. Now, if you look at it, we have 18 meters on one side, we have 2 meters on the other side. Now, the first thing we are going to do, what is the distance from this load to this point? You can see it from here. This is where the load stops. So what is left over here is 8.3. So similarly, like we did in the first one, we are going to use a similar triangle principle. Okay, so the first thing we are going to do, let's do the ratio. We have y2, this is our y2, we call it y1, y2, y3, y4. These are the ordinates of this influence line diagram. Okay, so we take the ratio. The first ratio we are going to have y2 over 1.8 equals to 16.2. You can see our 16.2 here, 16.2 to this point. That is for y2. We have from here to be 10.1. We have from here to here to be 8.3. So when we do that, we're going to have y2 over 1.8 equal to 16.2 over 18. We have y2 to be 1.62. Similarly, we do that, y3 over 1.8 becomes equal to 10.1 over 18. That gives us y3 to be 1.01. Then we go to y4. It becomes y4 over 1.8 equals to 8.3 over 18. That will give us y4 to be 0.83. Now we've gotten all the ordinates of this particular load arrangement. Now let's go over to the moment. Of course, the moment at axle 1, moment due to axle 1, remember the loads are here 4p, 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 4p. It becomes what? 4p times the ordinates of axle 1, which gives us 7.2. Moment 2 becomes moment due to axle 2, becomes the ordinate at axle 2. Ordinate at axle 2 is y2. We have it as 1.62. So it becomes 4p times 1.62, which gives us 6.48p. The second one is moment at axle 3, which it becomes 4p times the ordinate axle 3. Axle 3, the ordinate at axle 3, the ordinate is y3, and it's equal to 1.01, and that gives us 4.04p. The next one we have here is y4, which becomes moment due to y4 becomes the load at y4, which is this, times the ordinate at y4, which is 0.83. That gives us 3.33p. Now, having gotten these various moments, let's sum it up. If we sum it up, we are going to have it to be 21.04p kilonewton meters as the moment due to this arrangement. Now, let's try the second arrangement. The second arrangement is when we are going to place the second axle on this same point. Remember, the point is 0.1 L, where L represents the span of the beam. And that gives us that will give us from 0 to 2 meter point, which is this point. So look at the second load position. Now the second load position, our direction of travel still remains from the right hand side. We are moving to the left hand side. Now we have the load as this. We have 4p, 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 1.8, 6.1, and 1.8 respectively. Now you can see the load, the wheel, the axle load, the axle point, axle 1, axle 2, axle 3, and axle 4. Now the next position is to position this load with axle 2 at point 0.1 L, which is also the same as 2 meters away from support A. Now, if we do that, 2 meters away from support A, we station this load as this. You're going to have from here to the first axle to be 0.2. You're going to have here to be 10.1, which is the fourth axle. From support B to the third axle will be 11.9. All right. So using the principle of similar triangle, we can determine the ordinates of these various points. Let's call the ordinate at under Y1, under axle 1 to be Y1, that of axle 2 to be Y2, that of axle 3 Y3, that of axle 4 Y4. If we do that, we go by similar triangle to determine this. This is already known, this is unknown, this is unknown. So by similar triangle, we're going to have this as y1 over 1.8, y1 over 1.8 equal to 0.2 over 2. That will give us y1 to be 0.18. Similarly, y3 over 1.8 equal to 11.9 over 18. That will give us y3 to be 1.19. Similarly, we do the same thing for y4. We'll have 1.01. Now, having gotten these ordinates, the next step we are going to take is to determine the moment due to each of these concentrated load. And how do we do that? We multiply each of the load by the ordinates of the influence line under that load. Now we'll say 4P, moment due to axis 1, this is axis 1, let's call it M1. Moment due to axis 2, let's call it M2, axis 3, M3, axis 4, M4. Now, moment due to axis 1, axis 2 is this. It becomes 4P times the ordinate, which is 1.8, gives us 7.2P. Moment due to axis 1, it becomes Y1, becomes Y1, which is the ordinate 1 times 4P. That will give us 0.72P. Now, moment due to axis 3 becomes Y3 times the load at point 3, which is 4P, and that gives us 1.19 times 4, and it gives us 4.76P. Now, the last is axis 4. A moment due to axis 4 becomes the ordinate at axis 4, which is 1.01 times the load at point 4, which is 4P. That will give us 4.04P. By the time we do a summation of these values, we have that the total moment at that point, at this point, becomes 16.72P kilonewton meters. All right. So this is the total moment due to this load position on that point, 0.1 L of this beam. Now, we go into the fourth. Let's look at the third position. From the diagram on the board, you can see the third position. You observe that at the third position of load, the load is already driving towards this direction. Remember, the vehicle is moving in this direction. Okay. When the vehicle moves, the next position will be that axis 3 should be placed at 0.1 L, which is at the point 2 meters away from support A. By the time we place the axle load at that point, you will observe that the first and the second axle are already out of the beam. So we're only left with axle 1, we're only left with axle 3 and axle 4. And of course, axle 3 and axle 4 only has 2-point loads. And these 2-point loads cannot produce moments that will be greater than any of these two we have treated before now. So by that, we'll now conclude that putting axle 3 at that point 0.1 L is not necessary. It's just a waste of time. So what we have done using the first load arrangement and the second load arrangement is more than sufficient enough to determine the position of maximum moment of that point. So we cannot conclude that the moment at point 0.1 L, which is 0.2 meters away from support A, is 21.04P, knowing fully well that we have 16.72, which is lesser. This one gives us more moment. So it means that this load arrangement should be neglected. It cannot produce the maximum moment. What will produce the maximum moment at that point is this particular load arrangement, which is the first load arrangement we have taken. And that arrangement is when we have the first axle at that point. All right. So this is the arrangement that will produce the maximum moment at that point 0.1 L. And that value for maximum moment is 21.04P. So I believe with what we have done, you will be able to calculate the moment at any point on a simply supported beam carrying series of concentrated moving loads. It doesn't matter how the loads are, whether they are symmetrical or they are not. You can do that conveniently. You can take the third position, which is 0.3 L, and analyze that to check the position of the load and the value for the maximum moment at that point 0.3 L as an exercise for yourself. All right. So this brings us to the conclusion of today's lecture. I want to encourage you to like. If you enjoy what we have done, please click the like button or do where to subscribe. Our next lecture is going to be the design of a simply supported bridge. We're using what we have gotten to determine the position for maximum moment manually, and we're going to do it using the computer analysis method. Thank you very much. Stay cool.